Well, good morning and welcome to Doc Ontko's physics tutorials. My name is Keith Ontko, and this morning what we're going to be looking at is electric forces. In another topic we'll be looking at electric fields, but electric fields and electric forces fall under the topic of electrostatics. But today we want to specifically tackle electric forces. Well, as we know, as you've learned before in chemistry, we can have different kinds of charges. We can have positive charges, we can have negative charges, all right, and we can have neutral charges. Okay, positive charges and negative charges are a little more interesting because they do things, they can interact with each other. Neutral charges don't typically do a lot of interaction, although they can, depending on the situation. But today what we want to look at is we want to look at the interactions between positive charges and negative charges. As it's been discussed in the past, if I put a positive charge, like over here, next to a negative charge, what's going to happen is that these charges are going to want to move towards each other, right? Because positive and negative, or unlike charges, are attracted to each other. But as we learned quite a while back in Newton's laws, Newton's first law says that an object in motion will stay in motion and an object at rest will stay at rest unless acted on by some unbalanced force. So if we can imagine that these two charges, the positive and the negative charge, were initially at rest, and then somehow we were holding on to them or we let go of them, all right, they're going to start accelerating towards each other. They're going to start moving. So what must exist for that to happen? Well, there must be a force on each one of those charges. And indeed there is a force, and it's called Coulombs force. And there's a force on each charge due to the other charge. So there's going to be a force, an electric force, on the positive charge due to the negative charge. And Coulomb's law says that the value of this force is going to be an equation that looks like this. K, which is Coulomb's constant, times Q1, the value of the first charge, times Q2, the value of the second charge, divided by the distance between them. And that distance is, we call it R, sometimes it's called D. So it's given a variety of different letters, but we use R here. And so this is Coulomb's law. Okay. And we're going to use this to solve all the problems in forces. Now, of course, we can have more than two charges, but first we want to see if we can tackle two charges and what happens. As we also know, anytime we have a force, we not only have the magnitude of that force, which is the amount of the force, the number part of the force, but we also have a direction to that force. So force, any force, is a vector. And so when we deal with forces, we have to treat them as vectors. And when we add them or subtract them, we can't just add them or subtract them algebraically like we would do with, quote, normal numbers, but we have to add them or subtract them or put them together as we put vectors together. And so we have to use vector math. So we have to keep that in mind as we're dealing with these forces. So if I can have three different kinds of options here. I can have like charges where they're both, say, positive. I can have unlike charges where we have one that's positive and one that's negative. And again, I can have like charges again where they're both negative. And what we have to realize here is when we have a problem like this, when we're looking at just two charges, and by the way, anytime we're solving a problem like this, we only look at two charges at any given time. Okay, so that's going to be a rule. So if I asked you, if I called this 1 and I called this 2, and this is going to be 1 and this is 2 and this is 1 and this is 2, so I have all these pairs of charges. If I said, what is the force on this charge due to this charge over here? So what's the force on 1 due to charge 2? Well, the question I would have to ask myself is what is the direction of charge 1 going to be? Which way is it going to want to move because of charge 2? And the answer is because positive charges repel, right, or like charges repel, charge 1 over here is going to want to go to the left. Right? It's going to want to get away from charge 2. And by the same token, charge 2 is going to want to go to the right because it wants to get away from charge 1. So if I'm looking at the force on 1 due to 2, that force is going to be to the left in this particular case, right? In the case where we have both charges are like. Now what happens when we have one like charge and one unlike charge? Well, again, I have to look at what's going to happen to one charge because of the other charge. So what's going to happen to charge number 1 over here, the positive charge, due to charge number 2, which is the negative charge? Well, these are going to be attractive, right? And so charge number 1 is going to want to go in this direction, right? And so what's the force on charge number 1 going to be? The direction of the force? It's going to be to the right. Charge number 2, on the other hand, is going to want to go to the left because it's going to be attracted to the positive charge to the left of it. Okay, and so that would be the situation for case number 2. For case number 3, it's going to be the same as case number 1. These charges are both negative. They're going to repel each other, right? So the force on charge 1 is going to be to the left. The force on charge 2 is going to be to the right. Why do I mention this? Well, A, it's important to know this, and B, when we plug values into Coulombs' law up here, we're going to get some kind of an answer. And that answer could be positive and it could be negative. And the reality is that the number, the sign of the number that we get is meaningless. It doesn't give us any real indication as to the direction of the force because the direction of the force is totally dependent on the individual charge, right? In fact, I could plug in the values for the first situation here where I have 2 positive charges. I'm going to get a positive number for Coulombs' law because all the values are positive. But depending on which charge I look at, if I want the force on charge 1, well, that vector is going to be to the left. If I want the force on charge 2, well, that vector is going to be to the right. So does the sign of the answer give me any indication as to what the force is going to be? Well, no, it doesn't. It doesn't help at all. Okay. So let's do an example here. Let's say I've got 2 charges, and let's say they're both positive, and let's say that this is 2 microcoulombs, and this is 3 microcoulombs. Okay. And the first thing I'm going to do is I'm going to set up my equation. But first I'm going to write the equation with the force letter here, right, the force variable. And I'm going to say, well, first of all, which of these charges am I looking to get the force on? Well, I would like to know the force on this charge right here. Okay, I'd like to know the force on the 2 microcoulomb charge. So the convention that I use is I'll use a little subscript here. The force on charge, I'm going to call it, well, we can call this 2. The force on the 2 microcoulomb charge due to the 3 microcoulomb charge is equal to something. All right? And so this way, when I use the subscripts down here, I know which one of these I'm talking about. Okay? Because as we add more and more charges to this mess, right, it's important that we keep our accounting right. Here's another thing I'm going to do before I start plugging in any values. Right? I would like to know what the direction of this force is going to be. Right? It's not quite as important when we only have 2 charges, right? Because I have a force on this charge and it's due to this charge and that's really it. But as we get more charges into the configuration, it does make a difference. So I would like to know the force on the direction of the force on this. Well, these are both positive. This is going to be repelling, and so it's going to go off in that direction. So I'm going to draw a little vector above my force variable like that. So later on, when I go to use this, I know what direction that force is going to be in. So now let's plug the values in. Well, the standard value that we have for K is 8.98 times 10 to the 9th. All right, and I'm going to leave the units out because it just makes the equation that much longer. All right, times the value of the first charge. Well, it's going to be 2 times 10 to the minus 6th coulombs, and again, I'm going to leave the units out because this whole equation gets very long, times the value of the second charge, which is 3 times 10 to the minus 6th coulombs. And I'm going to divide that by the distance between them. Well, I didn't give a distance between them, so let's say that this is 4 centimeters. Okay, it's 4 centimeters. Remember, we have to convert centimeters to meters. That's going to be 0.04 meters squared. And again, I left the units out. I know this is not always the way many physics teachers like you to do things. They like you to include the units, but for brevity, to keep this equation fitting on the page, I'm leaving the units out for right now. And when we plug all this into our calculators, what we get is 33.67 newtons. So this is the force between these two charges. And this is a one-dimensional example. We only have two charges, and these happen to be, say, in the x dimension. All right. So what do we do if we have a problem that is in more than one dimension? So I'm going to just scroll my screen down a little bit here. Oops. Scroll this down a little bit here. And let's say that, again, I'm going to write Coulomb's law up here. So F is equal to K times Q1 times Q2 divided by R squared. Okay. What happens if now I have a positive charge here and a positive charge here and say a negative charge over here, and this is going to be 2 times 10 to the minus 8th coulombs. This is going to be 3 times 10 to the minus 8th coulombs, and this over here is going to be negative 4 times 10 to the minus 8th coulombs. Okay, and the distance between these is going to be 1 centimeter here and 1 centimeter here. So what have I got? Well, I no longer have just a one-dimensional problem. I've got a two-dimensional problem. And I would like to know what the force is going to be on this corner charge due to the other two charges. So how do I handle this? Well, the force, the net force, is going to be the vector sum of the force on the first charge, and I'm going to call this charge 1, this will be charge 2, and this will be charge 3. It's going to be the vector sum of the force on 1 due to 2 plus the force on 1 due to 3, right? And it's going to be vectors. And we have to remember that we have to add these as vectors. If I look at 1 and 2 here, what's the direction of the force on 1 going to be? 2? Well, we have a force on 1 due to 2. 1 and 2 are both positive charges. So which way is 1 going to want to go? It's going to get pushed in that direction. So the force is going to be down. Okay. I'm also going to have a force 1, 3. Right, the force on the corner charge over here due to the negative charge over here. And which way is that going to want to go? Well, this is attractive, right, because they're opposite charges. And so this is going to want to pull to the right. Okay, and so when I do the vector math later, I know that force 1, 3 is going to be in the positive x direction. Force 1, 2 is going to be in the negative y direction. And what I like to do is I like to get into a habit of creating a table somewhere maybe over on the left-hand side of my page, and I start adding up all of the x and y vectors, all right, and components of vectors, so that I can then finally get my resultant when I'm all done. Okay, it just makes the accounting a little bit easier. So what's the force on 1 due to 2 going to be? Well, it's going to be K, which is 8.98 times 10 to the 9th. And I know sometimes people round that up to 9 times 10 to the 9th, and that's just fine. Times 3 times 10 to the minus 8th times 2 times 10 to the minus 8th coulombs divided by the distance between them. Well, that's 1 centimeter, so 0.01 squared. Okay, and we're going to get some value for that, which we'll get in a minute. And then we can also calculate the force on 1 due to 3. That's going to be 8.98 times 10 to the 9th power times 3 times 10 to the minus 8th power times 4 times 10 to the minus 8th power. And notice that I left the sign off. And why did I leave the sign off? Well, because it is meaningless, as I mentioned before. All right. You have to visually inspect the situation to determine which direction the force is going to be, and we've already determined that. So let's come up with the value. So the values for these, I calculated the first one's going to be about 0.08 newtons, and the second one's going to be 0.1 newtons. Okay, and so now what I'm going to do is I'm going to add these to my table over in the lower right hand corner. The first value is going to be a negative y value. Why? Because it's going in the y direction and it's pointing down, so it's going to be negative. So this is going to be negative 0.08 newtons. And this value over here is going to be positive 0.1 newtons. Okay, and these are the only vectors that I have. So what can I do? I can now create a triangle and come up with my resultant vector using the Pythagorean theorem. Well, what have I got? Well, I've got a vector going in this direction. Whoops, I'm sorry. A vector going in that direction that is equal to 0.1 newtons. And then I've got a vector going in this direction, which is 0.08 newtons. And using the Pythagorean theorem, right, I can get the resultant of this, which turns out to be about 0.128 newtons. Okay, and so we added those as vectors. Okay, so it's important to keep the accounting right, because the more charges that we get into our situation, the more difficult it's going to be. If you'd like to see some examples of some more complex situations, please watch the videos under the video lessons and video examples, and I have some more of these examples where I have 3, 4 charges in different configurations where we solve those. Well, thanks for watching, and I hope you have a great day, and I hope this helped.